You know, every single day, millions of us step into a little metal box and just trust it. We trust it to lift us sometimes hundreds of feet into the sky. But have you ever stopped to think about the absolute powerhouse doing all that work? The unsung hero hidden away in the machine room? Well, today we're going to pull back the curtain on the incredible world of the elevator motor. So to really get what makes these motors tick, you got to think about two completely different kinds of strength. First, you've got your sprinter. We're talking incredible explosive bursts of power, but only for a few seconds. That's peak power. Then you have the marathon runner. This is all about sustained endurance, just chugging along for the long haul. That's continuous power. Now here's the crazy part. An elevator motor has to be both of these every single trip all day long.
And believe it or not, this battle starts way before you even press a button. Even when that elevator is sitting perfectly still, there's a constant, invisible tug-of-war going on behind the scenes.
This constant tension has a name. It's called static force, and it's all because of the weight difference between the elevator car, the part you're actually in, and this massive block of metal at the other end of the cables called the counterweight. But this is where the engineering gets really, really smart.
See, the counterweight is designed to weigh about the same as the empty elevator car, plus roughly half of its maximum passenger load. It's this brilliant balancing act. It means the motor almost never has to lift the full weight of the car. It just has to manage the difference in weight, which makes the whole system super efficient right from the get-go. Okay, so that's the story when we're standing still. But what happens the moment we start moving? Well, a single trip can actually be broken down into 4 distinct parts, and a whole new set of forces comes into play. The second the brakes release and that car starts to move, the motor has to deal with what we call dynamic forces. These are the extra challenges that pop up only when things are in motion. We're mainly talking about inertia, the resistance to getting started, and the friction of the car sliding up and down its guide rails.
So, step 1, acceleration. You know that little lurch you feel right as the elevator starts moving? That is the motor in full-on sprinter mode. For those first few seconds, it is fighting everything at once: the static force, all that friction, and the inertia of the entire system. This right here is its moment of maximum effort, its absolute peak power demand.
But after that initial burst, we hit step 2, constant speed. Now that we're just cruising along, inertia isn't a problem anymore. The motor can kind of breathe a sigh of relief and settle into a nice, steady effort. All it's doing now is managing that static imbalance and the friction. It's just humming along.
Now this next part is, I think, the coolest part: deceleration. As the elevator starts to slow down, that same inertia that was so tough to overcome at the beginning, well, it actually starts to help the motor. And get this, modern motors can actually act like a tiny power plant here. They become a generator, capturing the momentum of the slowing car and feeding that energy right back into the building's electrical grid. The elevator is literally helping to power itself down. How cool is that?
And finally, we have step 4, the stop. The journey's over, the heavy-duty mechanical brakes clamp on, and the motor's power usage drops to basically 0. It gets a tiny little moment of rest before it has to do that whole 4-step dance all over again, maybe thousands of times a day.
And that, right there, is the real engineering puzzle. I mean, analyzing one single trip is interesting, but building a motor that can do this over and over and over again without breaking a sweat, that's a whole different ballgame. This is where we stop thinking about the sprint and start focusing on the marathon.
So here's the million-dollar question. A motor might have the muscle for that initial sprint, sure, but can it run a non-stop marathon of trips all day, every day, without overheating? Because heat is the #1 enemy of a motor's lifespan. The answer to that question lies in a special value called RMS power. RMS stands for root mean square, but you can just think of it as the motor's true marathon rating. It's a really clever calculation that figures out the effective, average power over one complete work cycle: the acceleration, decruise, the slowdown, and the stop. And that final number tells engineers exactly how much heat that motor's going to generate over the long haul.
Whoa, okay. Now don't let the math on this slide scare you. What's really important here isn't the formula itself, but what it represents. This thing is like a perfect snapshot of the motor's entire journey. It takes the power used in each phase and multiplies it by how long each phase lasts. It gives engineers one single, powerful number to predict how the motor will perform day in and day out. And here it is, the golden rule of picking an elevator motor. The RMS power you calculate for the job has to be less than the motor's official continuous power rating.
That's it. This one check ensures you've picked the right marathon runner for the building, one that can handle the daily grind without burning out.
But you know, the math is just the beginning. As experts in the field, like the team at Noveen Puya Lift, often point out, selecting the absolute perfect motor requires a final checklist that goes way beyond just the numbers.
Right, so the pros, they run the numbers, but then they go through a whole checklist. They look at the service factor. That's a safety buffer for any unexpected overloads. They check the insulation class, which basically tells you how much heat the motor's wiring can take. They'll use super high-efficiency motors to cut down on wasted energy and heat. They make sure the cooling system is up to the task. And finally, they ensure the motor and its electronic brain, the drive, are in perfect sync. Each one of these is another layer of safety and reliability.
So the next time you step into an elevator and feel that gentle push as it starts to move, you'll know exactly what's happening. That's the sprinter handing the baton over to the marathon runner for the long, steady climb. It's a beautifully engineered dance between power and endurance, happening just out of sight every single day.